Good morning. We are approaching Christmas at high speed. Let me first return to the quiz that we had last week. As I told you, when we had the first quiz about radiation processes, the point of the quiz is not to make any kind of grades or something like that, but to see where you are, and for you to see where you are, and for me to see where you are. Now, to put it mildly, I was surprised to see the result. Now, to perhaps improve the way how you can locate where you are, let me go through the questions again and indicate what I thought would have been the correct answers. And in 3 out of 43 cases there were. I mean, in 3 out of 43 cases, all answers were correct. Gulp. Yes, question number 1. What is the essential difference between a gas and a fluid? Single correct answer. In my view, the correct answer is the mean free path of fluid particles is microscopically small. Remember what we said about the scale hierarchy for a fluid and so on. There's a microscopic scale, a mesoscopic scale, and a macroscopic scale. And the mean free path is so short that we don't notice it. That was question number 1. Question number 2, what is the essential statement of the equations of hydrodynamics? Single correct answer. And the correct answer is mass, energy, and momentum are conserved. All right, question number 3, what are the conditions underlying the Lane-Emden equation? Multiple correct answers possible. Okay, the 2 correct answers are adiabatic conditions. Right? That's what we assumed in order to relate pressure to density, and spherical symmetry and hydrostatics. Other answers are partly correct, but not fully. All right, question number 4. What is the essential statement of Bernoulli's equation in stationary conditions? And the correct single correct answer, which is the sum of specific kinetic energy, enthalpy, and gravitational potential is constant along flow lines. And ultimately, question number 5. How do stability analyses proceed? That's the cookbook. Multiple answers possible, and the 3 possible, the 3 correct answers were perturbations are decomposed into plane waves, the relevant equations are linearized in the perturbations, and stability is indicated by positive squared frequencies in a dispersion relation. All right. Given the distribution of answers, I suggest that you go through these questions again. All right, where were we? We are here. We talked about collisionless plasmas, and the essential point was that we first of all introduced the Debye length or the Debye wave number equivalently, and the plasma frequency, and today we are going to use them, or to need them again desperately. Then we talked about electromagnetic waves in media, and that was the main content of last time, and about dispersion relations. That's, yeah. We wrote down a very general formula for dispersion relations, namely that from 2 ingredients, one of which were the Maxwell equations, and the other one was our assumption of linear response, right? That the dielectricity is a linear, is given by a linear response of the medium to an externally imprinted electric field. D is epsilon E, right? That was our assumption of linear response. And from these 2 ingredients, we derived a matrix equation looking like matrix times electric field equals 0. And of course, right, this has non-trivial solutions, so solutions different from E equals 0, only if the matrix has a vanishing determinant. Otherwise, you can invert it, and then the trivial solution is the only one. So the propagation condition, or the general recipe for acquiring a dispersion relation then, was to set the determinant of that matrix to 0. But this, at that point, was a more or less empty statement, because that determinant contained the dielectric tensor, and we had no idea how to get at that. So our next step was to find out how we could derive the dielectric tensor under specific conditions, and this is where I would like to restart again today, hoping that we would at least arrive at specific dispersion relations for longitudinal and transverse waves in the course of this week, but maybe a bit further. All right, before we restart, do you have any questions about what I just summarized from last time, or anything else? If this is not the case, then let me return to several relations that we had arrived at last time. And first of all, I'm writing down our linear response assumption again. D is epsilon E, allowing that the dielectric function here could be a tensor. I told you last time we have no reason to believe that in non-magnetized plasma, the non-magnetized isotropic plasma, there should be any preferred direction. Right? But nonetheless, epsilon in general is a tensor. That was one way of writing this down. The other way of writing this down was D is E plus 4 pi p. Right? This is the another way of writing the same thing, namely that in a medium, the external electric field is superposed by the polarization that the electric field creates in the medium. And we had another relation which we are going to make use of, namely that the time derivative of the polarization is the polarized charge current. Okay. So far, so good. Okay, and then we said, now we need to approach in some way what the dielectric function could be. And we started with Liouville's equation for electrons. Proceeded along the same way as always, right? Brought the Liouville equation into linear form in perturbations, and then decomposed the perturbations in plane waves, right? So we started with Liouville's equation in this form. We said F is going to be some unperturbed phase-space density F0 plus a perturbation, and then linearized the Liouville equation in the perturbations to arrive at this equation. Okay, that was our conclusion from this whole procedure, except for decomposing delta F into plane waves yet. But what did we find, or what did we use? We used that the external force or the Lorentz force exerted by the external electric field creates a small perturbation. Right? This is in line with our assumption of linear response. But since this is the case, since this is a small quantity, or supposed to be a small quantity here, we have the momentum space gradient of the unperturbed phase space distribution here instead of F0 plus delta F. Remember also that we said in an isotropic medium, the gradient in momentum space of F0 is parallel to the momentum itself. Right? And you can see that by saying that in an isotropic medium, F0 will be a function of the absolute value of P only and not of the direction of P anymore. And if you now take the gradient with respect to P of this function, you will first get a derivative with respect to P square, and then a derivative of P square with respect to the momentum, which gives you 2P. And that will be parallel to P. And this allowed us to discard the magnetic part of the Lorentz force, because that would also, that would be perpendicular to the velocity, therefore perpendicular to the momentum, and therefore return 0 if we take the scalar product with the momentum. All right. So that was the equation we arrived at before decomposing delta F into plane waves. Then I did decompose delta F into plane waves and said, okay, the time derivative now will return a factor of minus I omega. And as last time, I'm going to write the plane wave components with the same symbol as the complete phase space perturbation delta F. All right, then the spatial gradient gives a factor of ik, where k is the wave number of the perturbation. So that gives me plus ik times the velocity times delta F. And on the right-hand side, we leave everything as unchanged, like that. So now, what is this? Right? This is an algebraic equation for the amplitude of a plane wave created by an external electric field in the electron phase space distribution. Okay? And it's important to recall that F here and the delta F are quantities of phase space densities for the electrons and their perturbation. All right. Okay, fine, but now we can just solve for delta F here, and we get, let me write the gradient with respect to P just in this way here, dP of 0, and now divided by I times kV minus omega. All right, but now we have almost everything we need. Because now if you want to calculate, for example, the polarized charge density, then what do we have to do? This is a perturbation of the phase space distribution. So if we integrate that over the momentum subspace, this will be a spatial number density fluctuation. And so the polarized charge density in the electrons will be minus E times the momentum space integral over delta F. That's that. With that, we could already continue, but it's easier to continue like that. I calculate in much the same way the polarized current density, which now, of course, is the charge density flowing. So this has another factor of v in here, of the velocity here. All right, and now I'm going to use that this polarized charge density here, polarized charge current density, is the time derivative of the polarization. Right now I'm walking my steps upward here. So this is dTp, but now I have to also express the polarization in plane waves. And if I take the time derivative, this corresponds to having minus I omega times the polarization. But now I have the polarization. All right. So this means that I can write the polarization as E over I omega integral d3p velocity times delta f. Okay. And now let me assemble these two equations. So now I'm going to insert this specific form for the phase-space fluctuation delta f with that specific form here for the polarization. And I'm doing that because delta f evidently contains a factor of E that I will then be able to factor out from this equation here, such as to identify the epsilon. Okay. So P is E over I omega times E over I. So that's minus E squared over omega. All right, then I have a momentum space integral. And now we need to be really careful. There's a factor of V that gives the polarization P its vectorial character. But then we do have a scalar product here. And I'm writing this in this particular way here. And I need to divide by kV minus omega. Hope it's complete. Okay, now I want to pull the vector E out of that integral. Okay, I'm going to write down what that then is. Minus E squared over omega d3p tensor product of V with dpf0 kV minus omega times E. Okay, if you decompose the tensor product into components, you see that its components will be Vi times the J component of dpf0, which will have to be multiplied with the J component of E because we have the scalar product of these two. And so that's exactly what we have to represent. But now I have this expression here manifestly in tensorial form. And of course that was what I was striving at. Now I only need to combine, finally, E and 4 pi p, and then identify everything that multiplies E with epsilon. Okay? So, in that way, I'm getting, first of all, an E, which I'm going to write as unit matrix times E, but the E will come at the end, okay? minus 4 pi times p, that's 4 pi e squared divided by omega, integral d3p, v tensor dp f0 divided by kv minus omega. And all of that is going to be multiplied with E. And now we have our dielectric tensor. That is the dielectric response function. So let me write this down in a box, because this is now what we are going to use multiple times. That's the dielectric response functions, or it's often called the dielectric tensor, or if you talk to somebody who comes more from the side of statistical physics or plasma physics, dielectric response function. Very important. Again, what ingredients did we use? Maxwell's equations, of course, right? And the assumption of linear response. Both together give you this function. Of course, a plasma can react differently, right? If you expose it to a very strong electric field, linear response will be no realistic assumption anymore. Also, we have used the collisionless version of the Liouville equation here. Right? There are no collision terms on the right-hand side. This means that we are effectively assuming that the plasma is dilute. Right? The number density of plasma electrons will not be very high. So for a dilute plasma, this is okay. If you had a very dense plasma, you would have to take into account that there will be Coulomb collisions, first of all, between the electrons and the electrons, and the electrons and the ions, and so forth. Right? So there are simplifying assumptions in there, but nonetheless, for dilute plasmas, under linear response, this is the dielectric response function here. All right. Isn't that beautiful? There's one problem. As we integrate over the momentum, sooner or later we will hit a singularity here. This means that in order to calculate this integral, we will have to analytically extend it into the complex plane. This means that the dielectric response function will acquire an imaginary part. And this leads to damping, as we will see. Right? This is called Landau damping. We'll see about that. But in general, we have to be rather careful with this integral here, right, because of this singularity here, which is inevitable as we integrate over all momenta. Okay, now, we had a technique developed for projecting out parallel and perpendicular components of a tensor. Let's apply that now. Let's write down a longitudinal dielectric function, which, by the way, will carry all the imaginary part. And how did we get that? That was the trace of the perpendicular projector times the dielectric tensor. Sorry, the parallel projector, oh, goodness. All right. Remember, this was the unit vector in k direction tensorial multiplied with the unit vector in k direction. So this is a parallel projector with respect to the perturbation in the wave vector of the perturbation in the phase space density of the electrons. Okay, I'm going to use that in the following form. It's 1 over k square vector k times vector k. So then I can pull the k square, 1 over k square out. And then from multiplying this object here, k times k, to that matrix, I will first get a scalar product of k times v and a tensor product of k times gradient p f0. Let me write this down. So I need to multiply k times k with v times dpf0. And by the rules of matrix multiplication, we will first have to take the scalar product of k times v, right? These two. And what remains will be a vector product of these two. Sorry, tensor product. Okay, so that's going to be vector k times v times k times dpf0. But now you take the trace, right? And the trace amounts to converting this into a scalar product, right? Because here you have ki times dpf0j. If you take the trace, it will be ki times dpf0i. And that's just going to be the scalar product of these two. All right. So carrying all this out will lead to, first of all, the trace of the parallel projector applied to the unit matrix. That's one. Lovely. Okay, now we have minus 4 pi e squared divided by omega k squared. That's the normalization of the projection tensor here. And then we have integral d3p k times v. I'm putting this in parentheses for a reason. And now k times dpf0 divided by k times v minus omega. All right, that's our longitudinal dielectric function here. Now let's massage this a little bit, because we can simplify this with respect to the common k times v expression in the numerator and denominator in the integrand here. So let me continue here. So epsilon parallel is going to be 1 minus 4 pi e squared divided by k square omega. Okay. Now integral d3p k times v minus omega plus omega divided by k times v minus omega plus nothing, k times dp f0. Okay. So I'm looking at the first term in this sum, this artificially created sum now. That's just a factor of 1. If I look at that only, then I have to integrate this 1 over k times dpf0. The integral does not depend on k, so I can pull the k out and integrate only dpf0 over d3p. That's a boundary term at infinity, a boundary term on f0 at infinity. If we assume that our electrons do not have infinite momenta, that's going to be 0. So the first part here integrates to 0, and we can drop it. So I can move on. This is 1 minus 4 pi e squared divided by k squared, because now the omega cancels here in the second term that remains. And I have d3p k times dp of 0 divided by k times v minus omega. All right. That's our longitudinal response function. Now, of course, we can create a transverse response function in exactly the same manner, and that's what we are going to do later. I would just have to take this tensor here, and now take 1/2 the trace of pi perpendicular times epsilon, and the 1/2 because our perpendicular projector was a projector on a two-dimensional subspace. Now, if you apply that, you will get a 1 here, and a 2 pi e squared divided by omega, and then we will just convert this v and this dp f0 here into their perpendicular components, and then we can go on as usual. But we'll do this in detail later, because for the moment I just wanted to have a bit fun with f, right? Fun with the longitudinal component of the dielectric function. Because first of all, having longitudinal electromagnetic waves is something strange. I would like to understand this better. Now, I told you before, and we'll see this later, first of all, this tensor here, the dielectric tensor, must catch an imaginary part, right, because of the singularity in the integrand. This imaginary part will stick exclusively to the longitudinal dielectric function. This is the point that I'm just claiming. You'll see that later. This gives rise to damping, right? So longitudinal waves are going to be damped. This is Landau damping, and now we are going to work this out, right? The question is therefore, first of all, if I need to take into account that this epsilon parallel has an imaginary part, then I must be aware of damping. This is the first statement that we will have to prove. The second is then, okay, how strong is this damping? Okay. So Landau damping, and of course that's Lev Davidovich Landau, the one with the many books. And for that, we will need to digress a little bit, first of all, in order to understand the relation between dissipation and an imaginary part in a linear response function. All right. An electric field of strength E has an energy density of E squared divided by 8 pi. Why is this so? First of all, I hope you have been told so in your electrodynamics course. Second, if you doubt that, you set up the energy momentum tensor for the electromagnetic field and identify the 0,0 component. If you don't know how to do that, you need to revert back to Noether's theorems for a field theory. Nonetheless, that's a standard result, right? That's the energy density of the electric field, and I want to know how much of that is lost. Okay? Then, if the electric field, because of any imaginary part or any other peculiarity in the longitudinal dielectricity, electric field is going to go down, this will give rise to this degree of dissipation here, of energy loss. But there will be one more, namely one more term. The polarized charge current density, this will create, or this will cause ohmic heating in the plasma. Okay, and both of these terms together are called the dissipation of the electric field, or the energy loss in the electric field. Okay, and our first goal now is to see how this relates to the imaginary part, if present, of epsilon longitudinal. Okay, let's first work out that. That's going to be E times E dot divided by 4 pi. Okay, and for the second term, I recall that this is just the time derivative of the polarization. Okay? We saw that before, right? The response of the medium to the electric field creates a polarization, and we saw that the time derivative of that polarization is the polarized charge current density, J-pol. Okay. So obviously I can write this like that. But now you see, you multiply in a scalar fashion the electric field with E dot plus 4 pi P dot. But E plus 4 pi P is D, right? That's the dielectric response, dielectric displacement. So this is 1 over 4 pi E times D dot. That's nice, right? Okay. But now the problem starts, because now, of course, we want, first of all, to decompose the E and D fields here into plane waves again to see what the dissipation at a certain electromagnetic wave frequency would be. So for that, it is advantageous, as always, to write E and D as complex numbers. But then, of course, in general, the Q will also be complex. And this is something we do not want, right? We want the real part of that. Okay, now, we could do the following thing. We could write here E times epsilon E dot, and take epsilon dot into account and so on. And then take the real part, but that's going to be rather confusing. Before we do that, or instead of doing that, let's do the following thing. Let's replace E with 1/2 E plus E star. That's evidently the real part of E. Let's replace D similarly by 1/2 D plus D star. But we want D dot, right? Careful now, because as we take the time derivative of a plane wave, we get a factor of minus I omega down here, but here we have to take the time derivative of the complex conjugate of that, which gives you a factor of plus I omega down. All right, so this means that instead of D dot, we have to write 1/2 or minus I omega divided by 2. Now, D minus D star. Okay? Just because the dot returns a complex conjugate phase factor from the complex conjugate quantity. All right, now we reassemble things. And put them here and get Q equals 1 over 4 pi times 1/2 times 1/2, that's 1 over 16 pi. Prefactor is minus I omega. And then we have E plus E star D minus D star. All right. This is minus I omega divided by 16 pi. All right. E plus E star epsilon E minus epsilon star E star. All right, and now we get a beautiful variety of terms. Right? One class of terms will have E times E, that's E squared. If we decompose the E squared into plane waves, that's going to go with E to the power of 2I omega t. And if you average over time, that's going to be gone because of the oscillating phase factor. If instead I multiply E with E star, the phase factor is going to drop out. And that's not going to average away. So if I average over time, all the E or E star terms are going to go away because they oscillate. But the E star terms will remain. Now, what do we have there? That's the prefactor, all right. Now we have E absolute squared. That's the amplitude, all right. And then we have epsilon minus epsilon star. And here you have the imaginary part, right? And twice, in fact. The imaginary part of epsilon parallel. Okay, so this is minus I omega divided by 8 pi, imaginary part of epsilon parallel times E squared. This is an important formula, right? It tells you on a timely average, and this must be an average over many oscillation periods of the fields. Right? Because otherwise the E times E and E star times E star terms will not go away. All right, but if that is the case, if the averaging period is long compared to the oscillation period of the electric field, then you get this result here. That's 2I times the imaginary part. So we even get rid of the I here. Of course, right, we wanted to have a real expression for the time average dissipation. Now you could again combine the E square over 8 pi here and see that this is the electric field energy density. And then you see the dissipation is just the energy density times omega times the imaginary part of the longitudinal dielectricity. Are you okay with this? Yes. Yes, I chose the longitudinal part only because we will later see that it carries the entire dielectric, the entire imaginary part of the dielectric response function. We'll see this later, right? But for the moment, I'm just claiming that, and I'm restricting the analysis to that particular part. By the way, you could stay here, right? And then you would get the imaginary part of any component of the dielectric response function. There was another finger up here. Same thing? Okay. Good. Some of you looked a bit perplexed when I said terms like that are going to average out. The reason is that this is an amplitude squared times that. Right, and now you oscillate over, I don't know, my language module is somehow disturbed today. Not you oscillate over an integrand, but you integrate over an oscillating integrand. Okay, and that's going to go away. All right, this leads us to this expression here. And this leads us to Landau damping, but first of all, we'll have a break, okay? off. 5 minutes. Let's restart at 10:05. right. Time to move on. Now the question is, since we have this beautiful formula here for the dissipation, how do we extract the imaginary part from this expression here? Now I said we first of all acquire an imaginary part because we will run over that singularity here. So the trick is that we are going to shift this singularity out of the way by a small amount, by pushing it below the real axis. So we are going to carry out the following operation. Instead of kV minus omega, I'm going to use kV minus omega minus I delta. And later, I will have to take the limit of delta going to 0. Okay, now I want to know the imaginary part of that. For that, I'm going to extend this fraction just by kV minus omega plus I delta. So then, this will be this. Now we can easily identify the imaginary part, right? That's going to be delta divided by okay. So far so good. Now what is this? Well, suppose kV minus omega is not 0. Then of course this limit is 0. Suppose k minus v minus omega is 0. Then this limit is anything else than 0. Then we can show by integrating over, let's say, that this is pi. Right? The integrand integrates to an arctangent, and if you evaluate this arctangent then between these limits, then you will get pi. So in other words, this object here in the limit of delta to 0 is 0 everywhere except at this equals 0, but if you integrate over the entire domain, then it's going to be 1. So this is a delta function. Sorry, a delta distribution. Okay, so, and it's pi times that, okay, all right? So this is going to be pi times a delta distribution of kV minus omega. Isn't that nice? This is sometimes called Dirac's identity, although it's not the complete Dirac identity. But nonetheless, we can now insert this to find out what the imaginary part of the longitudinal dielectricity is. So because of that, because of Dirac's identity, the imaginary part of epsilon parallel, which is of course the imaginary part of the second term only, is going to be minus 4 pi e squared divided by k squared. Now an integral over d3p k times dp of 0 pi times delta d kv minus omega. All right. Now we are integrating over the momentum, but we have the velocity here as a variable in the delta function. So let's do the following thing in order to do this properly. Let us first of all orient our coordinate system in momentum space such that the x-axis points towards k. Right, since we will have to integrate over the entire d3p, we are free to orient our coordinate system as we like. But then the scalar product here will single out the x component of the momentum only. Here as well. Right? This will single out the derivative of f0 with respect to px only. In other words, we can carry out the py and pz integrals right away and create an averaged, that is, or let's say an integrated phase space density f0 bar that depends on px and that depends on px only. So this means defining this. Possible because we orient k parallel to ex. We can write the imaginary part of the longitudinal dielectricity as minus 4 pi e squared divided by k squared. Now, an integral over dpx only, because that is everything that remains, from minus infinity to plus infinity, over k times df0 bar with respect to dpx. And now, since px is the only variable that f0 bar depends on, we even have an absolute derivative here. All right, and this is to be taken at pi times. I'm bringing the additional pi out front, I have 4 pi squared. Now I have delta d of kpx divided by an electron mass minus omega. All right, now I have an integral of the form integral of something times a delta function of a times x instead of x only. So this is 1 over a times the delta function. So if I carry this out, this is going to be minus 4 pi square e square divided by k square. Let me collect the k factors in another way. Now I have a factor of k from here. I have a factor of me divided by k from transforming the delta distribution. The integral is gone, right, by virtue of the delta distribution, and all that is left is df0 bar with respect to px taken at px equals omega me divided by k. Okay? K cancels. Four pi e square me divided by k square df0 bar dpx. Let me call this px0. Saves chalk. Aha. This is negative. This is negative. Does this mean we gain energy from damping? Usually, the F0 bar as a function of px will go down with an increasing value of px. Okay, the higher the momentum is, the lower will be the phase space density. So this is typically a negative number, so this is typically positive, and Q is positive, and you lose energy. Okay? All right, now let us reassemble that. And say, okay, the Q is now. Let me just copy that. 4 pi square E square ME divided by K square dF0 dpx F0 bar. All right. This is Landau damping, right? This is damping of waves due to the phase space distribution of the electrons here in the direction, or the gradient of the phase space distribution in momentum space along the direction of the wave. And the reason for this damping is that the longitudinal wave will have to accelerate and decelerate charges in the longitudinal way, right, because it's oscillating longitudinally. And there will be more charges at lower momentum, or if the number density of charges changes with momentum in the first place, there will be more charges to accelerate by the wave than there are charges that do accelerate the wave. And then the wave will lose energy. And if you invert this, the reverse will happen. Okay? So, what was the message here? There's a curious damping mechanism which comes from the phase space distribution of the particles, that of the medium that the wave propagates through. Another important part of the message is Dirac's identity. And a third part of the message here is that dissipation is caused by an imaginary part in the linear response function. Yes. I understood approximately a third of what you said.
Okay, so speak a bit louder.
Yes.
Could you explain again how we got to the limit pi times the delta distribution? Because I didn't quite get why we took the integral from minus infinity to infinity to get pi of the small delta.
All right. So first of all, in order to carry this out, I need to push the singularity out of the way. I do this by this operation here. And then, if I carry out this integral, I ultimately need to take a limit for delta to 0. If I take the limit for delta to 0 and the imaginary part of that, I'm getting this. So I'm looking at this integral now, because I want to know whether this expression here, if integrated over, gives you some finite number. The reason is that I need to recognize for values of this argument here different from 0, this is 0 anyway. For values of this argument equal to 0, it will be something that I cannot say. in order to say that, I'm integrating over it to see whether it satisfies the defining criteria of a delta distribution. Yes? Oh, I'm sorry. That's what it should be like. Goodness. It's good that you ask, you see. This is becoming wrong and wronger. Forget about this, please. The key point is that you integrate over this integrand here in order to see whether the integral gives the finite result. And then you find, all right, the integral over this integrand here in the limit of delta to 0 gives you a factor of pi. And now you know two things about this limit. You know it's 0 everywhere except where the term in parentheses is 0. But its integral over a region that contains this point here is finite. So it satisfies the defining criteria of a delta distribution. All right? Complete Dirac's identity looks a little bit different. It does not only look at the imaginary part, but at the complete integral. The complete integral is then replaced by its principal value, and you get in addition this imaginary part. Satisfied? Okay. Good. That was the point about that. Now, let us return to the longitudinal dielectric function and then work it out for a thermal plasma. Right? So far we have not made any assumption about what the unperturbed phase-space distribution F0 of the electron should be. Now we are specializing that to a thermal plasma. So if I look at a thermal plasma, I can write F0 is the unperturbed number density Ne bar divided by square root 2 pi sigma squared to the power of 3 exponential of minus p squared divided by 2 sigma squared. That's a Maxwellian, right? And since I want to have a thermal plasma, the sigma squared is Me kBt. Okay, so that in the exponent I just have p squared divided by 2 Me kBt, right? So that I have p squared divided by 2m, that's kinetic energy, and this is set into relation with the kinetic with the thermal energy. All right, suppose I use that, then I can instantly carry out what dp F0 is going to be, and this is just going to be minus p divided by sigma square F0. Right, and here you see again that if you take an isotropic distribution like that, the momentum space gradient of F0 is going to be aligned with the momentum itself, as we said before. All right, and now we are going to insert this into our formula for the longitudinal dielectric function. So 1 minus 4 pi e square divided by k square, and then integral d3p k times p over sigma square f0 divided by kv minus omega. All right. So this is what we now have to carry out. But again, we are going to proceed in the same manner as when we dealt with Landau damping. Namely, we are going to orient the coordinate system such that the x-axis again points into the direction of k. Which means that I can write this without loss of any generality as, well, 1 over sigma square from here. Now, a lonely integral about over px. Now I have here k times px divided by the electron mass minus omega. And then I will need to integrate over dpy and dpz, the only factor in the integrand that does depend on py and pz. That's the f0. All right. But we have a Gaussian here. And the Gaussian factorizes in all components of the momentum. So it's a Gaussian in all dimensions. And this means that any integral over py or pz over the Gaussian will just return a normalization factor. So I'm going to use now that this integral here over f0 is just going to be an e divided by square root 2 pi sigma square without the cube here. Right? This we have just integrated away. But the rest is just going to be e to the minus px squared divided by 2 sigma squared. Okay, that's all we need. Now with that, I'm going to return down here. And now things become a bit more manageable. So then, I have epsilon parallel is 1 minus 4 pi ne bar e squared divided by k squared. 1 over sigma squared, 1 over square root 2 pi sigma squared. I'm leaving all of these factors for a reason. Otherwise, we could just combine them. And then we have k times px exponential of minus px squared divided by 2 sigma squared divided by k times px divided by me minus omega. And this needs to be integrated over dpx only, and we are done with py and pz. Now what do we do about that? I now need to make a lot of replacements. So let me first of all justify all of these replacements. And first of all, do you remember what kd was? Right? The Debye wave number. that was the square root of 4 pi NE bar E squared divided by KBT. Do you remember what the plasma frequency was? That was the square root of 4 pi NE bar E squared divided by the electron mass. I need to borrow a sigma from here, because here we have a prefactor of 4 pi NE bar E squared divided by sigma. So 4 pi NE bar E squared divided by sigma. This is square root 4 pi NE bar E squared divided by square root of ME KB T. Now you take one of these square roots for KD and the other one for omega P, and you see that this is just KD times omega P. Isn't that lovely, right? Our previous scales that we introduced for the plasma come out very naturally here. And I can write, okay, this is 1 minus KD omega P. This K goes away against one of those, so I have KD over K. And I have a factor of 1 over sigma squared. This is odd, but let's just leave it. And I have that left over. But now I can walk on and say, okay, this is an integral over dpx, px, exponential of minus px squared divided by 2 sigma squared divided by k times px over me minus omega. Okay, next step is that I want to make the argument of the exponential as simple as possible. So I give it a new name. The new name, misleadingly, is t, which has nothing to do with time, right? It's just a temporary integration variable. So then the exponential is just e to the minus t squared. All right, but then I get something odd in the denominator that I have to take care of, namely k times px over me. This is now k times square root times sigma divided by me times t minus omega. All right. I abbreviate this as omega thermal, a thermal frequency, times t minus y, such that omega thermal is square root 2 k sigma divided by me, and y is omega divided by omega thermal. Sorry. All right. Prefactors. Now, I need to transform the px twice. Each transformation to t gives me a square root 2 sigma, so this gives me a 2 sigma squared. That was the reason why I left this sigma over here. Then I'm going to pull an omega th, a thermal frequency, out. And all that is left is an integral over dt, and that runs from minus infinity to plus infinity, as does the integral over px. Now we have t times e to the minus t squared divided by t minus y. Now we'll see, this is a lovely function that comes out from here. But nonetheless, you see, this goes away. And we have the beautiful expression, this is 1 minus the square root extends over the pi, right? Good. So we have square root 2 over pi kd times k omega p divided by omega thermal times something awkward, namely that. And you see how beautifully the prefactor comes out, right? We have a ratio of wave numbers, we have a ratio of frequencies, so evidently this is dimensionless, and the rest of the integral obviously also is, because we transformed everything to dimensionless variables. So the whole function is dimensionless, as it should be, as long as we reasonably give d and e the same unit. Right? There are people who are of the opposite opinion, but okay. Now, let us have a look at this object here. And for that I need a new board. So let's have a look at this particular integral. And this won't take long. So we have to deal with minus infinity to plus infinity dt, t e to the minus t squared divided by t minus y. Okay, first we telescope, right? We replace the t by t minus y plus y. The first part gives us just an integral over the e to the minus t squared, which gives you a square root of 2, or a square root of pi. And then what remains is an integral over y times, y times the integral over minus infinity to plus infinity dt, e to the minus t squared t minus y. I was afraid of a sign error coming my way. But it has come my way long before. I think it's correct. So anyway. Now, I'm introducing a new function, which by and large is the only function that I know of that is named after a woman. W of z is I over pi z minus t. That's called the Faddeeva function. That has to do with the error function, that has to do with Dawson's integral, lovely classes of functions that are related to her. Now you see, this object here is minus pi over I times W of y. Okay. So here the z comes first. This is why the minus sign comes in. And by the definition of the Faddeeva function, it comes from a normalization condition, we have pi over I or minus pi over I or plus I times pi W of y. Okay? That's the Faddeeva function. Now, this is sometimes called root pi times z of y. This is now the plasma dispersion function. All right, so you can express this integral either by the Faddeeva function or, which is more common, by what is called the plasma dispersion function. Okay. So you see from there that we can write this integral minus infinity to plus infinity dt t e to the minus t squared divided by t minus y as root pi times 1 plus y times z of y. All right, and at this point we could right as well stop, right, because this function is available, right? For example, you can use the implementation of the Faddeeva function in Python, and then you can convert this to the plasma dispersion function. You can have a look at it. It has beautiful imaginary and real parts and so on and so forth. But for now, let us just insert this result insert this result down here. So then you see the square root of pi is going to cancel. And we can write this is 1 plus square root 2 kd over k omega p over omega thermal. And now what remains of that is 1 plus yz of y. Yeah, and now we have reached a beautiful goal, right? We have the dielectric, the longitudinal dielectric function for a thermal plasma, expressed by a function that is, implemented in many ways. Now you can just write these prefactors in a different way, and often you see them transformed. So suppose you take not the product of kd and omega p, the Debye wave number and the plasma frequency, but you take the Debye wave number and divide it by the plasma frequency. Why not? Right? If I take this then you see the 4 pi and e bar e square cancels out. And sorry, I wanted to take the inverse of that. Then I get square root of kBt divided by me. All right. Now have a look at the thermal frequency here, and write the sigma out. All right, that's going to be square root 2 times k, square root of kBt divided by me. Right? The sigma is square root me kBt, and so you see that instead of writing, or you can replace here the square root by omega thermal and say omega p divided by kd is the same as omega p divided by square root 2 k times omega thermal. This is one way of rewriting that. And this means that you could now replace the omega p divided by omega thermal by a square root 2 times k omega p divided by omega thermal. That's square root 2k omega p divided by kd. And you can insert this here, and the kd drops out, and the k drops out. And you get a factor that you cannot believe. There's an error somewhere. Let's leave it at this point, and I'm going to correct this next time. Let me very briefly show you an extension of the Jupyter notebook for the lecture, which now contains also the calculation of the plasma dispersion function. And then we are going to use this next time. All right, so here's the respective section here, electromagnetic waves in the thermal plasma. This is the definition of the plasma dispersion function here. That's the imaginary unit times the root of pi times wafts, and wafts is the Faddeev function, right, W of z. All right, and here is not the dispersion function alone, z of y, but y times z of y. Right? Because the same product as we had it here will also reappear in the transverse dielectric function, and this is why I plotted y times z of y directly. And you see, okay, there's a blue line coming up here, running through a maximum, getting flat. This is minus the real part of y, z of y. Okay, there's a dashed line asymptotically aligning with it. That's just the function 2y squared. So when we look at limiting cases, right, low frequencies, high frequencies, and so on, For a very wide range of frequencies, we can just replace y times z of y, or rather minus the real part of y times z of y, by 2y squared. Okay, lovely. Then we have the imaginary part, that's the orange line. It crawls up, it falls down. This also has an asymptotic limit, which goes like square root pi times y, also rather simple. Then you see at large frequencies, the imaginary part dies out completely. And what is the limit for the large frequencies? Well, it's approximately y equals 1. And then the absolute value of y times z of y, that's the green curve, aligns with the real part and the imaginary part is gone. Okay. Then also for this part here, for the high frequency part that turns flat here, we can find a useful approximation, because as you see in this plot here, what I'm plotting here now is not y times z of y or minus the real part of it or so, but minus 1 minus y times z of y. Okay, so that's the difference between minus y times z and y and the flat 1 part here. Right? So what distinguishes from 1 is this curve here, and this just goes like 1 over 2y squared. So it goes like 1 over 2y squared for high frequencies, and it goes like 2y squared for low frequencies. Well, this we can memorize, right? This is not so bad. All right, so even though this rather complicated looking plasma dispersion function appears here, right, in very many cases in astrophysical situations, limiting cases are enough, and then you can discuss low frequency, high frequency, dispersion relations and these things separately. And then you can get very interesting results out. For example, next time we are going to use the high frequency limit here in order to see how much an electromagnetic signal slows down when it has to run through a plasma. The so-called dispersion measure that appears there. And that slows down, for example, radio signals from radio pulses that we need to use in order to, or that we are using in order to detect gravitational waves. Right? So that's an important thing. All right. Wednesday, we have to talk about the transverse dielectric response function, which is even simpler than this calculation now. And then we have a lot of things at hand, right, is to study the propagation of electromagnetic waves, phase velocities, group velocities, blah, 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 in plasma. Thank you very much.